Preparing for a software engineering at Datadog interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you find the first non-repeating character in a string? I would solve this in 2 passes. First, I build a frequency map for every character. Then I scan the string again and return the first character whose count is 1. This preserves ordering while keeping the implementation simple. The time complexity is O, N, and auxiliary space is O, K, where K is the character set size. I would define behavior for empty input and clarify whether Unicode code points, rather than bytes, must be supported. While answering, explain the frequency map approach, 2-pass traversal, time and space complexity, character encoding assumptions, and how you would handle empty input or Unicode in production quality code. Question 2. How would you design a rate limiter for a high-throughput service? I would start with a token bucket because it supports controlled bursts while enforcing an average rate. For multiple service instances, I would store bucket state in a low-latency shared system such as Redis and use an atomic script for refill and consume operations. Keys could represent API keys or tenants. I would define behavior during data store failure, expose rejection metrics, and protect the limiter itself from becoming a bottleneck through sharding and local caching. Make sure to cover token bucket or leaky bucket algorithms, distributed state, atomic updates, client identity, burst behavior, fail open versus fail close decisions, and metrics for rejected requests and limiter health. Question 3. How would you design a metrics ingestion pipeline similar to Datadog's? I would place lightweight agents or collectors near workloads to batch, compress, and forward metrics asynchronously. A durable, partitioned queue would absorb bursts and decouple ingestion from storage. Consumers could aggregate compatible points, then write to a time series store optimized for tag queries. I would enforce cardinality limits, authenticate producers, and apply backpressure rather than allowing unbounded memory growth. Replication, retry queues, and ingestion lag dashboards would make failures visible and recoverable. In your answer, discuss agents, batching, buffering, partitioning, compression, backpressure, high-cardinality tags, durable queues, aggregation, storage formats, and how you would preserve availability during downstream outages. Question 4. What is the difference between metrics, logs, and traces, and when would you use each? Metrics are aggregated numerical measurements, so they are excellent for alerts and dashboards. Logs record detailed events and provide context, but querying large volumes is more expensive. Traces show a request's path across services and expose latency or dependency failures. During an outage, I might detect elevated error metrics, inspect traces to locate the failing service, and use correlated logs to understand the exact input or exception. Strong systems connect all 3 with consistent service and request identifiers. Be sure to mention aggregation, event detail, request causality, cardinality, retention cost, correlation identifiers, and examples showing how the 3 observability signals complement one another during incident investigation. Question 5. How would you investigate a sudden latency increase in a production service? I would first confirm the alert, compare P50, P95, and P99 latency, and determine which endpoints, regions, and customers are affected. Then I would correlate the timing with deployments, traffic changes, resource saturation, database performance, and dependency traces. I would use logs for representative slow requests, not just averages. Mitigation comes first, roll back, shed load, or disable a feature, followed by a controlled root cause investigation and a regression test or permanent guardrail. Focus on establishing scope and timing, comparing percentiles, checking recent changes and dependencies, using traces and saturation signals, reproducing safely, and distinguishing application, infrastructure, network, and data store causes. Question 6. Explain concurrency versus parallelism and how you would use them in a backend service. Concurrency means managing multiple tasks in overlapping progress. Parallelism means executing tasks simultaneously on different cores. I use concurrency to keep a service responsive while waiting on network or storage I/O, often with bounded worker pools. For CPU-heavy work, parallel execution can reduce elapsed time. I must protect shared state with clear ownership or synchronization, propagate cancellation, and limit concurrency so downstream systems are not overwhelmed. Profiling should validate that concurrency improves throughput rather than adding contention. Cover task interleaving versus simultaneous execution, CPU-bound and I/O-bound workloads, synchronization, race conditions, worker pools, go routines or threads, cancellation, and the importance of measuring contention. Question 7. What causes a data race, and how would you prevent one? A data race occurs when concurrent execution accesses the same memory, at least one access writes, and there is no valid synchronization relationship. The result can vary by timing and may escape ordinary tests. I prevent races by assigning ownership, passing immutable values, or protecting shared state with a mutex or atomic operation. In Go, I would run the race detector, add stress tests, and review lock ordering. The simplest safe design is usually better than clever synchronization. In your answer, define unsynchronized conflicting accesses, distinguish atomicity from visibility, discuss mutexes, channels, immutable data, race detectors, test coverage, and minimizing shared mutable state. Question 8. How would you make an API request safely retryable? I retry only failures that are likely transient, such as timeouts, connection resets, or selected 500 responses. Exponential backoff with jitter prevents synchronized clients from creating a retry storm, while deadlines and a retry budget cap total work. For writes, I require an idempotency key so the server can safely recognize duplicates and return the original result. I would measure attempts, exhausted retries, and added latency, because retries can hide an overloaded dependency. Discuss idempotency, retryable status codes, exponential backoff with jitter, retry budgets, deadlines, duplicate side effects, idempotency keys, and observability for retry volume and downstream pressure. Question 9. How would you design a distributed job queue? I would persist jobs in a replicated queue and let consumers claim them with a visibility timeout. A worker acknowledges a job only after its side effects succeed, otherwise the message becomes available again. Since at least once delivery can duplicate work, handlers must be idempotent, usually through a job identifier or deduplication record. I would use partitions for throughput, accept that global ordering is expensive, and monitor queue depth, oldest job age, retry counts, and dead letter volume. Make sure to cover producers, consumers, durable delivery, visibility timeouts, acknowledgements, retries, dead letter queues, ordering, partitioning, idempotent handlers, and monitoring queue age and processing lag. Question 10. How do you choose between SQL and NoSQL for a new service? I choose from access patterns and correctness requirements, not popularity. SQL is preferable when relationships, transactions, constraints, and flexible queries matter. A NoSQL store can fit predictable key-based access, massive horizontal scale, or specialized time series workloads, but usually requires denormalization and careful consistency decisions. I would estimate read and write volume, data growth, recovery needs, and operational expertise. A relational database is often the best starting point until measured constraints justify added complexity. Focus on access patterns, consistency, transactions, schema evolution, joins, scaling model, operational maturity, query flexibility, and whether the workload is relational, document-oriented, key-value, or time series. Question 11. What is eventual consistency, and how would you explain its trade-offs to a product team? Eventual consistency means replicas may temporarily disagree, but they converge if updates stop. It can improve availability, latency, and geographic scalability, especially for feeds or telemetry where slight staleness is acceptable. The product team must understand visible effects, such as a newly created item not appearing immediately on another device. I would provide read-your-rights behavior where possible, document freshness guarantees, and retain strong consistency for payments, authorization, or invariants that cannot tolerate conflicting decisions. Be sure to explain stale reads, convergence, availability and partition tolerance, user-visible consequences, read-your-rights options, conflict handling, and where strong consistency remains necessary. Question 12. How would you reduce high-cardinality problems in an observability system? High-cardinality occurs when dimensions such as request IDs or arbitrary URLs create huge numbers of unique time series. I would keep bounded tags like service, region, and status, while moving per request details into logs or traces. At ingestion, I would enforce quotas, normalize paths, aggregate where appropriate, and reject or downsample unsafe dimensions. I would monitor series growth and query cost, then give teams clear feedback so governance does not become an unexplained production failure. Discuss why unique identifiers create expensive series, distinguish useful dimensions from unbounded values, use aggregation and sampling, enforce quotas, and preserve debugging value through logs or traces. Question 13. How would you roll out a database schema change without downtime? I use an expand and contract process. First, I add nullable or otherwise backward-compatible schema elements without removing old ones. Then I deploy code that can read both versions and gradually backfill data in small, throttled batches. After validation, I switch reads, enable new writes, and monitor errors and replication lag. Only after all consumers migrate do I remove obsolete fields. For large tables, I use online migration tools and keep a rollback path at every stage. In your answer, describe expand and contract migration, backward-compatible application versions, backfills, dual reads or writes, online indexes, validation, rollback, and avoiding long blocking locks. Question 14. What makes a service resilient to dependency failures? A resilient service assumes dependencies will be slow or unavailable. I set explicit timeouts, use bounded jittered retries only for safe operations, and add circuit breakers to stop wasting resources on a failing dependency. Bulkheads isolate worker pools, while fallbacks preserve limited functionality when possible. I also propagate cancellation and expose dependency-specific metrics. Finally, I test outages, latency, and partial failures in staging or controlled experiments, because resilience is behavior that must be verified. Cover timeouts, bounded retries, circuit breakers, bulkheads, fallbacks, health checks, graceful degradation, dependency budgets, and testing failure modes rather than relying only on happy path tests. Question 15. How would you design an efficient log search system? I would collect logs through agents, attach tenant and service metadata, and partition storage primarily by time and tenant. Recent data could use fast indexed storage, while older data moves to compressed lower-cost tiers. An inverted index supports field and text searches, but I would avoid indexing every unbounded field. Query limits, cancellation, quotas, and shard pruning protect the cluster. I would optimize common queries first and track ingestion lag, index size, and search latency. Make sure to discuss collection, parsing, indexing strategy, inverted indexes, partitioning by time, compression, retention tiers, query limits, tenant isolation, and balancing search speed against storage cost. Question 16. How do you review code for correctness and maintainability? I first understand the intended behavior and examine tests, interfaces, and failure paths before commenting on style. I look for incorrect edge case handling, unsafe concurrency, unclear ownership, security risks, and missing observability. I ask whether the design is simple enough to maintain and whether performance claims have measurements. My feedback is specific and prioritized, blocking correctness issues first, then risks and improvements. I also recognize good decisions, because collaborative reviews produce better outcomes than adversarial ones. Focus on behavior, edge cases, failure handling, tests, API clarity, concurrency, security, observability, performance evidence, and whether the change fits existing conventions without unnecessary scope expansion. Question 17. Tell me about a time you debugged a difficult production issue. In one incident, API latency rose after a seemingly harmless configuration change. I compared deployment timing, traces, and database metrics, then found a new query path bypassing an existing index. I rolled back to stabilize customers, communicated updates in the incident channel, and reproduced the issue with production-like data. We added the missing index, a query performance test, and an alert on percentile latency. The lesson was to validate operational impact, not just application correctness, before rollout. Be sure to structure the story with context, impact, hypotheses, evidence, mitigation, root cause, communication, and follow-up prevention, emphasizing calm ownership and measurable results. Question 18. How would you test a distributed service beyond unit tests? Unit tests validate local logic quickly, but distributed behavior requires integration tests with real dependencies or faithful substitutes. I add contract tests for service boundaries, property-based tests for parsers and invariants, and load tests for throughput and tail latency. Fault injection covers timeouts, duplicates, partial outages, and delayed queues. I make tests deterministic with controllable clocks and isolated data. Production metrics, canaries, and replayed incidents then close gaps that test environments cannot model. Discuss unit, integration, contract, property-based, load, fault injection, and end-to-end tests, along with deterministic clocks, test environments, data cleanup, and measuring reliability signals. Question 19. How would you improve the performance of a Go service? I would measure first using representative benchmarks and CPU, memory, blocking, and allocation profiles. Common wins include eliminating unnecessary allocations, reusing buffers carefully, batching I/O, reducing lock contention, and setting sensible timeouts. I would inspect Go routine growth and garbage collection behavior rather than assuming more concurrency helps. After each change, I would compare throughput, P95 or P99 latency, memory, and error rate under realistic load. Readability and operational safety remain more important than marginal micro-optimizations. In your answer, mention profiling before optimization, CPU and memory profiles, allocations, garbage collection, blocking I/O, Go routine limits, batching, caching, and validating improvements with realistic benchmarks. Question 20. Why do you want to work at Datadog, and how would you contribute as a software engineer? Datadog interests me because observability sits at the intersection of distributed systems, developer experience, and real customer impact. I enjoy building reliable backend software where scale, latency, and correctness are visible in production. I would contribute strong fundamentals in APIs, concurrency, testing, and operational debugging, while learning deeply from the telemetry domain. I also value collaborative ownership, shipping incrementally, measuring outcomes, documenting trade-offs, and improving systems after incidents rather than treating them as isolated failures. Make sure to connect your motivation to observability, distributed systems, customer impact, engineering quality, collaboration, and a concrete example of skills you would bring to Datadog's high-scale environment. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.